Good evening to this special Astro Adda session, wherein there are a few of us, um some of us from Public Outreach and Education Committee, Astronomical Society, some of us, some who have been speakers in this 39th meeting of the Astronomical Society of India, wherein uh, for the year, many of the cutting edge astronomy endeavors have been reported. And here, this is the POIC's effort to try to ask all the speakers to come in and make what they have reported palatable at an outreach level. And we are going to get started with today's session was about transients at all kinds of scales. And one of the things which is very, very interesting to look at is that many of these kind of phenomenon are so ubiquitous everywhere. They're everywhere. And so in all kind of contexts, solar system, stars, galaxies, extragalactic, and so on. Many of these. And so one aspect of it, which is the changes, any kinds of changes that we see, and particularly sudden changes, transient changes. That is what was kind of celebrated in the morning session today. We have with us Professor Poonam Chandra from the NCRA, National Center for Radio Astrophysics, and using the upgraded GMRT and um, other cutting edge radio telescopes, um, Poonam looked at a kind of a detective story where, like in the Agatha Christie, elephants can remember 20 years later, one is solving the puzzle. So she has looked at supernovae for decades. So after a star has died. And by Poonam, after decades of these observations, you are actually going back and finding out about the star itself. What was the progenitor star like? What kind of mass may have come out of it over a period of time, and so on. So we are looking to you to tell the participants the clues to your detective story.
All right. Thank you, Ratnashri, and hello, everyone. And yes, indeed, it is a detective story. In fact, let me just tell you that in astronomy, everything is a detective story. The reason is that every single light photon you receive, the event has happened in the past. Even the sunlight takes 8 minutes for it to reach to Earth. So if something has to happen to sun right at this very moment, you will get to know only after 8 minutes, because that much time the information will take to reach. So the same here, these supernovae, uh, basically, let me just not say supernovae, but let me just give you a little glimpse of what I'm talking about. And I would like to put this slide to show you, because this is a very exciting slide. The massive stars in our universe are amazing stars. These are the stars which give rise to these transient phenomena. Means these transients are basically one of the most energetic explosions in the universe, and we call them supernovae or gamma ray bursts. And in fact, sometimes these supernovae and gamma ray bursts, after these supernovae and gamma ray burst, these massive stars would leave neutron stars and black hole behind, and sometimes they also undergo a second death, which we call sometimes in form of gravitational waves, sometimes short gamma ray bursts, sometimes light from the gravitational wave events, and so on. All of these things are transient because they change in the lifetime of in the human lifetime. The supernova event happen on the scales of, for example, hours to days to months. The gamma ray bursts from milliseconds to seconds to days or so on, which is very unprecedented in astronomy. So when we study these deaths of massive stars, we are not just studying the death of massive stars and trying to understand the stellar evolution. We are also trying to study the extremes of physics, because these are one of the most energetic explosions in our universe. So, and when I say the detective story, ideally, let me just show you this. Sorry, let me just go back to my very nice diagram or animation which I wanted to show. Yes. So let me just start with this. This is the supernova detected in our sky Uh, I don't know why it's not working. Okay. Since 1900 to until now, you can see the year at the later. Initially, we were scientists were detecting maybe one or two supernova a year or so. Now we have more better telescopes, automated robotic telescopes, and we are detecting so many supernovae. All of these supernovae announce the death of massive stars. And one of the major, biggest problem in astrophysics is to look at these supernovae and connect them with associate with them with the star which exploded at supernovae. And that is the research I am working on. And when Ratnashri said that collecting the data for 20 years like Agatha Christie, actually she is not joking, because indeed this is what we have done for some cases, and this is what I talked about this morning. So let me just, before saying that, let me just show you that this is how a star, massive star, will explode and become a supernova. And what I did, I studied this matter, explosive matter, and its interaction with the surrounding stellar winds. And since these surrounding stellar winds have these signatures, or you can call footprints, of these progenitor stars, I studied this ejecta interacting with these stellar winds for 20 years. And when I studied this for 20 years, this is what I got. What I got is that I basically, in the left plot, you will see at the center is your star which exploded at the supernova. The gray is the stellar wind which I was just talking about, and the green is the one which I was is a very dense shell. So when we uh, studied this supernova, which is called 2001 EM, when we studied for 20 years, what we realized that is supernova was not, the ejecta was not moving in a very smooth wind. The progenitor star was having a very glitchy kind of evolution, and that is what we try to understand. And what finally we understood by studying the data is that this is how a progenitor must have been. And I will tell you in a minute why, but let me just tell you what the progenitor was must have been. What we say is that there are two stars gravitationally bound to each other. Both of the stars are very massive, but the one which is more massive will explode as a supernova first. It will make a neutron star. The neutron star will come into the in spiral into the other big star, and this will accelerate the evolution of the other big star, and which will explode as a supernova. But because of this in spiral of neutron star, it will create a very non-smooth kind of stellar winds, and those stellar winds we were seeing. And in this way, numerical simulations have seen that at the equatorial disk you will have very high density. So what I am showing you here is this is what we saw. And left plot you may probably find it little difficult to understand, but you can see the images on the right. So if you see the top image, the emission is in radio band, and what it shows, it is showing us these ejecta interacting with stellar wind. But as you go down, you will see that the emission starts to get weaker at the pointed emission, and this diffusion kind of starts to come up. Now you go on the right top, you see that the second blob is appearing, and then eventually it is getting brighter, and the first one is going away. So the second peak in the left light curve is this second blob which is getting brighter, and that is the equatorial disk matter. And such equatorial disk matter can only be created in this common envelope scenario. So this is how, when we studied this supernova for 20 years, we were able to in some way, like a Sherlock Holmes, try to we just had the data after the supernova explosion, and we could go back to the supernova and try to understand how, what kind of star system must have exploded to make this exotic supernova. uh, I
Yes.
guess that answers your question, Ratnashri. If you have any other question, please.
Yeah, you had see, these are supernovae which are a little different from the. I mean, a large number of other supernovae where these are from stars which don't have their envelope and so on, and which don't have their hydrogen or helium and outer shells, right? And so these are somewhat peculiar kind of supernovae, but not what are called Wolf-Rayet or the Type 1b or those kind of supernovae. So there was something peculiar about these. Also, you were finding somewhat late kind of time when the radio enhancement and
Yes.
these things were happening. So, would you like to tell something about
Yes,
that?
yes. I would, let me just explain that, and let me just open this slide. So this is how a star evolves in our universe. A star produces radiation by nuclear fusion of elements. And for example, in sun, hydrogen is fusing into helium. But since these stars are so big, it just doesn't end into hydrogen burning into helium, but even the more progressive and heavier element also does the nuclear fusion and hydrogen into helium, carbon, neon, oxygen, silicon. And finally, this nuclear fusion ends when there is iron at the core, because iron cannot burn into anything, fuse into anything heavier and release energy. So it means it is at that point a star will not be able to sustain its gravitational collapse against the radiation pressure, and basically it will become unstable. But what happen, and that is when the supernova explosion will happen. But in between, what happens is that this star is so big in size that outermost layers are less gravitationally bound to the star, and the star will keep on losing these outermost layers. And in some cases the mass loss rate is so much that it can lose its all of its hydrogen envelope, and it will just, if you look at this star, you will see only helium and beyond, and surface you will only see helium. But there are some exotic massive stars which are supposed to be very massive, or in binary systems, where because of the binary stars, uh, the star which is going to explode as a supernova is not just going to lose hydrogen, but it is also going to lose its helium envelope. And this is how the star will look like on the rightmost column. So if you look at, if suppose you could look at this star, you could look all the way to inside, you would not see on the rightmost star, you would not see the hydrogen, you would not see the helium, you would see only the static group carbon oxygen and beyond. Now the thing is that not every star can will have a carbon oxygen, not every star will have hydrogen intact, which means a star will become a peculiar particular supernova based on its property. So depending upon which star we are observing, which supernova we are observing, whether we are observing a supernova which is, we call it stripped envelope supernova, which does not have hydrogen or helium, it will have a different implications on the progenitor. And this is the supernova we observed, the one which I'm calling type 1c on the right. But this was not a very pure type 1c supernova. The problem was that this was, when the supernova exploded, we thought it is a supernova which has only bare carbon oxygen, and in the spectra, optical spectra, there was no hydrogen. But people didn't give up, they kept on taking the data, and then they realized that 3 years down the line they are seeing the signatures of hydrogen. Now if hydrogen is there in a supernova, it becomes a type 2 supernova on the left side. It means it was this special supernova which made its transition or metamorphized from a type 1c or stripped envelope supernova to hydrogen rich supernova. And what we say and we understand or we explain it is that hydrogen envelope got lost from the star. Okay, even the helium envelope got lost, and that hydrogen and helium envelope was moving with some slow speeds, say 10 to 50 kilometers per second. And then the supernova explosion happened, and the ejecta happened with 5-6 thousand kilometer per second. And within 3 years, it caught up to this hydrogen shell. And once it caught up to the hydrogen shell, we started seeing the signatures of hydrogen in the spectra, and we said that it has become a type 2n supernova. So this is the story of this particular supernova.
Yeah, actually, given that we are kind of giving small nuggets to everyone, so we are not really going into the nitty gritties of how exactly you did your detective work to go back to. Pratik, did you have any questions Poonam. And Amit, I am adding you in the stream. Uh, so we'll wait for Amit to.
But
Yeah,
maybe
I
I can
don't.
let me just take
Yeah.
2 minutes
yeah,
to just put everything in perspective since we are
Yes,
not
please do, please do, please do,
explanation.
please
Okay.
do. Because we
So
have done small by small bits. Please do
yes,
that.
so let me just do that. So what happens? Let me just say that massive stars are extremely important part of our universe, and they in some way they decide the nature of the universe because these are the only star where this heavy nuclear fusion are happening and these heavier elements are getting created. There is no other place in the universe where such elements are getting created. So these stars do enrich the galaxies where they reside with these heavy elements without which the human life is not possible. So it is very important to understand these stars, and these stars can enrich the surrounding with these heavy elements only after they have exploded at supernovae and the elements which were being formed inside the star got scattered in the medium for us to become available. The good thing is that all of these big stars will explode, will die with a big explosion, which I said supernova or sometimes gamma ray bursts. And what my point here is that it is very important to understand or in some way the map a individual massive star to what kind of supernova it will become. And we do not have too many tools to do that. We cannot sit and watch an evolution of a full star because star will live for millions of years and we won't. So the best we can do, what we are trying to do, we are studying the supernova in radio band. We are studying the effect of the supernova ejecta interacting with the winds which carry the information about the star, and we are retracing those winds and trying to tell about star. So basically, in some way, we are moving from right to left because we do not have a channel to move from left to right. And this is the big problem, and this is the big problem we are trying to address in different ways and trying to increase our sphere of our knowledge. I think this is a way I can put this whole field into perspective.
Thank you, Poonam. And if there are any questions any of us would like to ask Poonam and Amit, if we could have you come in, so we will go on to one more aspects of the transient phenomenon which are so ubiquitous everywhere. And Poonam, if you could be there for some time, I would ask both
Yes,
you
sure.
and
I will be
Amit.
there for 5, 10
Uh,
more
uh,
minutes.
uh, uh, yeah, Amit, we will have your discussion about the Blazar observations which you had
yeah.
reported. But before that, perhaps if you and Poonam could help us get a little bit of an idea about one other transient talk which was there in the morning today, wherein so many aspects of transient phenomena were discussed. So, if you and Poonam could walk us through that, and then we will come to the Blazar 3C279. Yes, we'll come to
Sure,
that
sure. So we
after you
can
walk
do
us
that.
through that.
I hope I can share some presentations using this share button. Right? I have never used this
Yes, yes,
platform, so
yes,
let
yes.
me try.
So,
Uh,
you could add screen share, and I will add it in the window, and then I will ask
let
you
me
and Poonam to walk us through.
yeah, let me just try it out. Uh,
And so while that's if there are any questions any of us would like to ask, please. Uh, for those of I mean all of us who are here in the studio, sometimes if you are not present in the window but you would like to ask a question,
There
you
is a
make
question
your
from there is a question from Ranjit
yeah, there
Kumar,
is,
and I
yes,
can
yes,
quickly
yes,
answer that.
yeah,
He is
yeah, please go
asking
ahead.
if there is any other method except nuclear fusion for stars to release the energy. The energy generation in stars happen only via nuclear fusion. That is when they are still evolving. After their death, the radioactive decay can also release energy, but not during when the stars are evolving. At that time, it's only the nuclear fusion which is the one. Amit, all
Before
yours.
I hand
Yeah.
Before I hand
Yes,
over to
please.
both of you, I just wanted to tell all our colleagues who are in the studio. So, if you are not present in the window, if you wish to ask a question, maybe if you will just put your video on, I will know that you want to ask a question, and then I could add you, because right now only I am able to add to the window which is visible. So, this is my request to every one of us who is in the studio. If you have a question, you put your video on. I will know you want to ask a question, and I'll hand over to yeah. And where is the screen share? I don't see the screen share, Amit, yet. For me to add to this, when you are doing the screen share, is it is it a Linux system? Then maybe
It's a
it is better to do full screen share rather than a tab, or maybe better. Yeah, yeah, I see it. I see it now. I see it now.
all right. But
It
now
will
I
be
cannot.
coming in. Yes, it has come in.
But I cannot see you, but I can see my screen, which is fine with me.
Yes, yes, yes,
All
yes.
right.
And if we are not able to hear you, also I will come in and.
Sure, sure. That would be great. So, uh, Poonam, shall I start a bit what Nayantara today has tried to
Of
explain?
course, all yours. Please, if you
Okay.
want to just
Thank you very
do it.
much.
Yeah.
So today, Dr. Nayantara Gupta discussed a few aspects of very high energy and high energy astrophysics, where mostly her expertise on the neutrino physics, which is we call it astroparticle physics, where we try some of these uh, try some particle physics technique to do the astronomy or astrophysics. And today she talked about one of the telescope which is called Fermi-LAT. This is telescope which is operated by NASA. So in 2008, they have sent it in the orbit, and this telescope detect a very high energy gamma ray, and high energy gamma rays above uh, 20 MeV or 20 million electron volt. Or so the why we need this kind of telescope. First of all, why we do have an optical telescope and we can study several sources. As I have just mentioned or shown in one of the corners of my slide, an optical image taken by Hubble Space Telescope, which is an optical telescope, and it's a deep field image. Uh, so if we go out using a telescope or even in the night sky, what we see are stars and galaxies. However, once we try to see once we try to see the sources in different wavebands. It means these sources are not restricted to emit only optical light. They can emit X-ray light, radio light, where Poonam focus mostly, and sometimes the gamma ray light or gamma ray photons, where I mostly work on. So when if you do that, what you actually see in the sky, or if I just say if I project the universe on a plane, then how gamma ray sources will be distributed. So on the right side there will you see a oval shaped map where there's a lot of blue color, which is a sort of a background, and then you see some bright red dots and a straight line. So this straight line is our own galaxy, which is showing in the red and yellow color. And this particular image is a 3D image. It has a 3D projection, and it has a lot of small sources. Some of them are galactic sources, which could be pulsars or supernovas or our own galactic center, and some of them are below this line, which we call it galactic plane, and above to the galactic plane. And these are the mostly extra galactic sources, the galaxies, some active galaxies which emit gamma rays. And today Nayantara discussed about these different type of sources, and she also talked about whether these sources show some transient behavior. It means whether they vary over the time. So if I go out and use my telescope, let's say for me today and after 10 days, whether the flux changes. So this is somewhat a transient phenomena. And uh, let's say if I do it in gamma ray waveband or gamma ray energies, we generally, or till now, we have detected almost 6 to 7,000 sources which are associated to gamma rays. And in today's talk, Nayantara actually classified some of them with this particular image, where you can see our own galaxy has some sort of bubbles, which we call it Fermi bubble. And she talked about it, that how these bubbles are emitting, what are the mechanisms by which radiation is emitted. So some of these things she has discussed. One of the most interesting thing about the Fermi bubbles are that it is believed that these jets are the failed, sorry, these bubbles are the failed jets. It means at some point in the past, it was these two bubbles were actually trying to be a jets. However, due to some certain mechanism which we do not understand now, they couldn't become a relativistic jets, but they still have a some sort of a remnant. So this is a very interesting thing. A lot of scientists are trying to learn why, how they are formed and how they are emitting. It is believed that with the presence of magnetic field, electrons interact with this magnetic field and they emit with synchrotron radiation and sometimes inverse Compton radiation, which is some sort of a scattering where an electron hits a photon to the higher energy. It's basically just kicking a low energy photon to a higher energy photons, and then you observe them in gamma ray. However, Fermi bubbles are not only observed in gamma rays, but they have a counterpart in almost all the energy bands, even up to the radios. However, that is uh, this particular thing maybe we can talk sometime else. But Fermi has also detected several other type of sources. They have detected pulsars. They have pulsar wind nebulae, even sun. And one of the interesting thing which I always find it very interesting, that our moon is more brighter in the gamma ray than the sun, which might have not been mentioned here, but very interesting. And there are some very so today she has talked about the transients. So there are possible transient in gamma rays. So most of the time the pulsar wind nebulae and supernovas are not a transient. They emit for a very long time, their flux does not change. However, there are transients such as gamma ray burst or active galactic nuclei, or sometimes the microquasars. These sources actually changes their flux or their luminosity over a short time scale, sometime over the day scale, sometime over the years scale, sometime even over the minute scale, and for the GRVs even order of a few seconds scale. So today the focus of Nayantara's talk was to understand these and to associate if there is a neutrino emission from these transients. So she wanted to learn using some of these experiments which are right now going to be installed in several part of the globe. One of these is Came3Net,
Uh,
discussed,
uh,
where
um,
the detector or basically the PMTs are laid in the Mediterranean Sea.
Amit,
And yeah,
Amit, sorry. Actually, Poonam had to leave, and she
sure.
wanted to put in something about from Nayantara's talk about
Sure.
neutrinos. Poonam, you wanted to
Yeah, maybe
uh,
Amit, I can just
put in
say a little bit about I can just give a little perspective of neutrinos, and then you can continue with the rest of the talk, since you talked about neutrino observatories. So I would
Yeah.
just like to tell all of you is that uh, light, or so far what we have talked about, whether it is radio emission or the Fermi bubble emission in high energies, everything is we are seeing is via photon. So this is one messenger of seeing our universe or knowing about our universe, but this messenger does not give the full information. For example, you can, from if you see the light, you can only see the outside of the sun, you will not see what is happening inside the sun. So it is better to have other messengers of light. And what Amit just talked about, the neutrino observatories, neutrino is another messenger of our universe, giving a very complementary information about our universe. For example, so far we have seen some neutrinos from our sun. We have seen the neutrinos from a supernova in large Magellanic cloud, and we have seen a moderately significant neutrino from a Blazar event. And the thing is that all of these neutrinos were produced via when you study quantum mechanics, a process called something called beta decay. And these neutrinos and antineutrinos were produced at the very, very core, very heart of the star, which you will never be able to see via light. But it is because of these neutrinos seen from the sun that we knew that hydrogen is being converted into helium when two of the proton has to become neutrons. Or inside the stars, when we got to know that these beta decay reactions are inside the supernova, when we saw that we confirmed a theoretical assumption, which means it is giving us another channel to understand the universe. Recently there was a, I think, 100 or 300 TeV, tera electron volt, that is a very very energetic neutrino, whereas in supernova you see million electron volt neutrino only. This tera electron volt neutrino was seen from a blazar using an instrument called ice cube, and this is telling us of these very very high energy transient phenomena for universe, and it is allowing us to probe a very heart of these objects. I think this is what I wanted to say, Amit, and then maybe you can take over now, because I just wanted to put this whole neutrino thing into perspective.
Sure, sure. You have just enlightened us about this particular aspect. I actually forgot to say a few things. Thank you very much, Poonam. Yes,
Sure.
so today's Nayantara actually shown a few movies also, that how these uh, detectors were laid in the sea, and uh, I think she is working on the Cam3 net, but there are another experiment called Ice Cube, which is at the South Pole, and there detectors are actually laid inside the ice, which detects a very specific kind of radiation, which is called Cherenkov radiation. And using that information, they try to learn about the energy and the direction of the neutrinos. And why neutrinos are important? Because they tell us much more than the photons, which Poonam told us, that it tells actually the which mechanism is responsible, exact mechanism, which is a bit difficult in the case of photons, because photons can be produced with the one of these mechanisms, and we cannot distinguish it. However, it is more easy to distinguish if we have a neutrino. So this is something today Nayantara talked about, and I think she also talked about Fermi bubbles, which I have already explained. Then she
Yeah.
also talked about this particular star. I think it's a binary system. It's a stellar system which is called Eta Carinae, and as I remember, she discussed
Yeah.
a few.
Yeah.
Yeah,
Sorry. I was just saying that, yeah, after Ita Karina, we will come to the Blazar.
sure, of
Yeah.
course.
Yeah.
Yeah.
Yes.
So I think, well, as I remember the talk, she discussed about this stellar system. It has a two stars, and uh, it was observed at the multi-wave band scenarios with different telescopes. And then what they have found in her research, that there is a contribution which cannot be explained with the known physics, or basically or known models. So they have to invoke some more interesting physics, which is a acceleration of protons or cosmic rays, and that if you add that contribution, then the observed light at the gamma ray energies can be explained, which is a very interesting uh, thing to know, that these sources may accelerate particles up to very high energy. I think this is what Nayantara discussed today, and now I will talk about what I have done or I have
Yeah.
discussed in my talk.
Yeah.
So,
Ac- Actually, yeah, yeah. You also had observations from the Fermi
yeah,
the LAT telescope, which was discussed a little bit. You are going to talk about observations of a blazar, so perhaps it would be useful to just let the viewers know blazar. And there are so many of these blazar, BLAC. What are the
sure,
quasar
sure.
connections of these objects? If you maybe get
I'll
started
do
with that.
I'll do that. I'll do that. So very quickly, as I have a Fermi-LAT on my screen, so Fermi-LAT is a telescope which detects gamma ray photon. So you cannot detect gamma ray photon just by using an optical telescope or a mirror, because gamma ray photon has so much energy, it just passes through the mirror, so you cannot focus it. However, there are ways by which you can actually make the gamma ray photon to interact with the matter and then produce electron positron pairs, and you use some detectors which we call it silicon strip detectors. You don't worry about them, but they give us some information about the direction and the energy, and energy can be computed using some other kind of detector which we call it cesium telluride detector. So you don't worry, but there is a different type of telescope you can think of. Now what I have talked about, let me try to uh, yeah. So this is what I have talked about, and I work on these systems. So, in our own universe, we have a very different type of galaxies. We have normal galaxies like ours, spiral galaxy, some of the irregular galaxies. However, if someone asks me that, can you classify galaxies in very simple way? Then I would say there are two type of galaxies. One galaxies which do not have any active central part, and the other ones which do have that central part. So the galaxies which do have this central region, which we call it nucleus, are called active galactic nuclei. And why they are called active galactic nuclei? Because at their center there is a supermassive black hole resides, and this black hole basically accrete matter, basically eat the matter whatever is in the surrounding. Most of the time, we have a accretion disk, a disk of a matter of the plasma. Basically, could be proton, electron, or some dust, and this particular disk basically circles this black hole, and most of the time black hole try to accrete the matter from that point, from that disk, and shines. So this accretion disk has a temperature of up to million degrees, and it shines almost in X-ray bands. However, sometimes we also see that there are some out very close to the black hole comes out through accretion disk, and these outflows are considered or called to be jets. And if these outflows are at the relativistic speeds, it means the plasma which is present in these outflows are moving with the relativistic speed. It means almost with the velocity of the speed of light. Then we call them relativistic jets. And when we consider these relativistic jets, a lot of gamma ray emission, X-ray emission, all the non-thermal emission is produced. Okay, so as Snehashri said about some of them are blazar, some of them are radio galaxies. So what happens? So as you can see on the left side, there is a image of a Centaurus. It's a composite image of a different, made with a different type of using different type of wavelengths, X-ray, radio, optical. So you can see a jet coming out, and let's consider if this jet is very close to the line of Earth, or it means we are directly seeing in this particular jet. If we have this kind of active galactic nuclei, we classify these sources as a blazars. And why blazar? Blazar is, the word comes from the blaze, where the things are basically uh, uh, overpower everything. So that's what actually happens. These jets actually overpower the light which is coming from the host galaxy, the entire galaxy, and that's why they are called blazars. And further, you can classify these systems into two different systems. One is flat spectrum radio quasar, another one is BL-LAT, depending upon whether they have some sort of clouds nearby their black hole or not. It is not very important, but you can just classify. If you know, then you can just classify them. So I work on them,
You
and
uh,
but
you
yeah,
observed the flares from these blazars, and you observed flares where there were kind of micro scales and macro scales put together,
right,
and and then you inferred that these are far away from this blazar, and but at the same location. And
right,
could you walk us through a little bit of how you
yes,
arrived at that?
yes. This is a very interesting story. So basically, the first optical jet or first relativistic jet was almost detected 100 years back in 1980. And from that time onwards till today, we do not have a very clear indication that how these jets are launched. There are several theories, but there is no observational proof which tell us that this mechanism has actually worked to launch a jet. It was a very long standing problem. In almost in 1980, Professor Roger Blanford suggested a model. However, the problem with that was of that model is was it was very elegant, but it does not have a much observational properties. So you cannot observe those properties. But with the help of a lot of simulations, people come up with some of these predictions. So Blanford and Znayak has proposed a model, and using some numerical simulation, MHD numerical simulations, some other scientists come up with a prediction. So what they have said that if you observe these kind of sources, these kind of blazars every day, or let's say over the long time, you have, if uh, these jets are formed through Blanford's Knight process, you should have detected one peculiar kind of behavior. And what is that peculiar kind of behavior? That if you take every night, you take an observation from, let's say, from Fermi-LAT telescope, what you will see, the flux will increase slowly for, let's say, for few days, and then suddenly flux will increase within few minutes, almost 2 to 3 times what it has already in this already has been exceeded. So let's see, it goes up to from 1 to 25 over the 5 days, but from 25 to 75 within few minutes, and then it has to come back within next 1 hour or 2 hour back again to 25, and then slowly again decay to 1 or 2 counts. So that kind of uh, model they have said or proposed, that if this particular jets are launched through this particular model, which is Blanford's Knight, then you should detect this kind of a change in the flux of active galactic nuclei. However, we had several telescopes. We tried very hard for 15 years, at least I started from my PhD, and now I'm a assistant professor. I have joined a faculty. Almost 15 years has passed, and after 15 years, we have able to observe one of these particular event, or I would say two. We have got two of these events, which actually suggest that yes, this uh, particular model is correct, and we actually detect this particular type of light curve, which is shown here. So if you see the image in right side bottom, there is a light curve, there is a time on the x-axis and a flux on the y-axis, flux or luminosity, whatever you call it. So basically the amount of light versus time, and if you plot, you will see in the blue points are slowly increasing with the time. So from it starts from 22 until 28, it reaches from 3 to 4 counts to almost 10 to 11 counts, but in next few minutes or within a few 1 or 2 hours, the flux increases to the almost 40, and then stays for some time and then come back, and then again slowly decreases up to the similar numbers which was earlier. So, and on the left side there is a prediction, so you can see we have actually found the predicted light curve from a certain model, which suggests that yes, it is possible. So it suggests that the launching of these relativistic outflows are due to Blanford's Knight process. However, as Ratneshi said, that we have said that they are very far away. How we know that it's not happening very close to the black hole? Why they are far away from the black hole? So these particular kind of sources, which we call it flat spectrum radio quasar, as I said, they have some clouds of the hydrogen atoms and molecules, and these clouds most of the time emit UV radiation, ultraviolet radiation, and there is a mechanism by which a photon can again interact with another photon. So in case of this particular active galactic nuclei, this UV photon from a hydrogen cloud interacts with the gamma ray photon and produces pairs. So if gamma ray photons are originated within this broad line region, within close to the black hole, let's say very close, let's say only few light years, even less than a light years away, then the gamma ray which is originated close to the black hole will be absorbed, will should have been produced pairs, and we should have not detected these gamma rays. Because we are detecting this gamma ray, it means the emission of the gamma ray should have been came out much downstream or much far away from the black hole, where the the radiation from from the hydrogen clouds are less, so there are no UV photons, and gamma rays can without interaction can leave that particular region. So that is why, because we have detected gamma rays, and we have found some peculiar pattern and a very sharp rise in the flux. All using all these characteristics, we have found that the emission should have been much far away from the black hole, not very close to the black hole.
Yeah, you have a kind of for each conclusion you arrive at different kind of observations and modeling you have combined together to say that the two are coming from the same place, far away from the blazar,
Yes,
and
yes,
also that if the energy is from what are called magnetic reconnection kind of
yes.
events. If we could let the participants know about that,
Right, right.
and also I'm thinking that this is so interesting. Perhaps at a later stage, more details we could give out to students. If you could also suggest some small quantitative explorations which they could do, we will do that as a full session at some time. If you could right now just let them know
Sure,
this
sure.
final conclusion, how you
We
arrived at that final
yeah,
conclusion that both are the same
we can do
place.
that. Yeah, we can do that. So now, the conclusion that why these two events are happening at the same place is very interesting. Okay, so now we have to understand how the gamma rays are actually produced. So, as I said, the gamma rays can be produced if an electron just kick a photon, or basically we call it inverse Compton scattering. The process is an electron which has some certain energy comes from the behind and hit this particular photon of certain energy. Let's say a radio photon or an optical photon which has a 1 electron volt of energy, and yeah, a photon of having a 1 electron volt of energy, which is an optical photon, let's say blue photon, and from behind a very high energy electron which has having a, let's say, 10 power 9 electron volt of energy, or 10 is power 10 electron volt of energies. It comes from behind and just hit this particular photon of optical wavelengths or optical energy. What happens once this electron comes and hit from behind, it transfers, electron transfers its energy to the photon, and the photon which was at the optical wavelength or optical energies actually get kicks, and its energy increases up to the gamma rays. So this is the process by which gamma rays are produced. Now, in blazars or in the active galactic nuclei, if you have to uh, produce gamma rays, then you require these photons which are having a low energies, like around 1 electron volt to 10 electron volts. 1 electron volt is optical light, 10 electron volt is a UV light, and if you go, let's say, 0.1 electron volt, it's around infrared. So it could be a little bit here and there, but more or less this is the scale. So generally what happens, as I said, the black hole is surrounded by accretion disk. So accretion disk emits mostly X-ray photons, and this accretion disk is surrounded by a torus, a dusty torus, basically a lot of dust, and this dust emits a photon of infrared energies. Once this infrared energies photons are present in the this region, what may happen that if you have an electron, then this electron can come and interact with this infrared photon and give us a kick, give a kick to this infrared photon, and up scattered it up to the high energy gamma rays. A very similar process can happen with the UV photons as well, which are produced by these clouds. So there will be a UV photon, and that will get energy from an electron. Now, there is a problem, a small problem, that the UV photons are only at a certain distance from the black hole. So it's like a very sharp, not very sharp cutoff, but a sharp cutoff, a cutoff. So from distance, let's say from the black hole to the some certain 0.1 parsecs. Parsec is a basically a length scale or a unit generally used. It's around 3 light years, you can approximately say. So if I say broad line regions are up to, let's say, 1 light year. Now these UV photons are actually contained in this particular region up to 1 light year, and afterwards there are mostly infrared photons which are coming from the torus. Now, what happens, how we come to the conclusion that this emission is taking place at the same location, the very sharp flare and the very slow envelope emission. See, once this interaction happens, if I if I take a different energy of gamma ray photon, which comes through these interactions, because there will be a number, the electrons will have a very different energy. There will be so many electrons, not one. So they will push different photons to different energies. So what happens, what you get is called a spectrum. So if I bin energy of each gamma ray photon in a small bin, then what I get, a spectrum. I try to see if I have one of them.
Yeah. And
Sorry, I do not
if we
have a
could,
spectrum,
yeah,
but
it's okay. If you could
but
just let
what
me
exactly
know, and
happens, that
we
it's some sort of hello, can you hear me?
conclude.
Yeah, all right. So hello, can you see me or hear me?
Yeah, yeah, we can.
Yes,
Ah,
yes.
yeah, sure. So basically, these photons follow some sort of curve, very basically, some sort of curve. And from these two events, which is a very sharp flare and slowly varying envelope, these two curves are very similar, and they are similar because the electrons which are present in both the places are interacting with the same photons, which are infrared photons, and that's why the curve is very similar, and that is why we can conclude that the place where they are interacting is same, the small region and the big region, and that's why they're co-spatial. And why, once they are co-spatial, then there is only one way to actually do that. And what is the way? That these blazars have an ordered field. So ordered field means, let's say if you take a water pipe and you just wind up, so what will have, water will flow in this, but at certain length, if you just simply shake this pipe, what will happen? The due to some disturbance, this water, the streamlined water will break into the small droplets. A very similar thing happens. There are instabilities, we call it instabilities. Due to these instabilities, this ordered magnetic pipe breaks into the small fields, and then this magnetic what so we get a lot of magnetic fields, and these magnetic field interacts and change their direction and topologies. And when this process happens, there is a origin of a new jet. So there is a small jet used to born in the very long relativistic jets. It's like a small blob. It's like, let's say if you are moving in a train and you just throw a ball. So this new ball is basically a jet. In our case, a jet of lot of magnetic energy, and that gives the rise to this very sharp and very bright gamma ray emission. And so basically, detection of these very fast and very sharp flares on a slowly varying envelope is a prediction from the Blandford's Knight process, where black hole is giving its rotational energy to the jet and getting slower and slower. So basically, what happens is shown here. So at the center of the uh, galaxy, you have a black hole which is rotating and producing a lot of magnetic field, and this magnetic field further down in the jet uh, getting breaks down into smaller pieces and producing these jets. So this is the phenomena, this is the theory which we have actually proven with the observations.
Yeah.
And
Thanks so much, Amit, for
yeah,
walking us through that detective story so far away from us and so far away from the star. And it's not
yes,
fair, perhaps, to have asked you to very quickly let us walk us through that. And I will be requesting Virendra Yadav. He wanted to share with the participants some aspects of instrumentation in connection with Virendra ji. You can put your screen share, and I will add it into the. If you have, you put your screen share. And meanwhile, I mean, while that is going on, anyone has any questions, etc. In fact, this story is so very interesting. I was very tempted to pull out aspects of it and put them in a planetarium show, because blazars
That
always
would be very,
interest
that would be very
students, even
nice.
when they are, I mean, have a little bit of an idea. Just the name itself excites them.
Sure.
So
Maybe we
Virendra
can
ji, I have seen your so
work
this
out.
is just added here, your screen share. And Amit, we will have a full-fledged talk about this at some stage
No,
as part
ma'am.
of
I will be
Astro.
glad to do that. I'll be glad to do that.
And after the instrumentation, we have also with us Soumyaranjan Das and Sushri Sangeeta, who will be taking us through the Sun and Solar System session, which was there today. But first, I hand over to you, Virendra Yadav, from Aries, the Nainital. Walk us quickly through some excitements of instrumentation which were discussed.
Ma'am, is this relayed on YouTube as well, or no?
Yes, it is going live on YouTube and it will be available later on as immediately after this as a recorded session.
Okay.
So, yeah.
Yeah, I had forgotten
Virendra, when
to
you are
turn my mic
using
on.
your presentation, when you are using your presentation, probably you will not be able to see the studio. But if you are not able
Yeah,
to hear you
yeah.
or so, I will alert you.
Yeah, no, I have started YouTube also side by side on mute so that if there is some issue, I'll come to know.
Yes.
Yeah.
There will be a
Okay.
delay.
Yeah. Thank you, ma'am. I attended some of the talks in this instrumentation session. Beforehand, I tell that I am not an engineer or even a professional astronomer. I am basically a space physicist. But we wanted to convey some of the exciting things that we came across in the instrumentation section or the talks, that I thought I'll share some of those with you. So first of all, there was one talk about 5 years of Astrochat by V. Girish from ISRO. Now you may have heard about Astrochat. It's a space-based observatory launched by ISRO, and there were a bunch of Indian astronomy research institutes who took part in this mission and developed this observatory. And it was launched in I think September 2015, and it has recently completed 5 years. So he just gave in sort of overview of Astrosat observatory and its mission status, and the output or research output that has been there till now. So I just thought that I'll briefly talk about what Astrosat is. So and basically, since it's a space-based observatory, so what was the need to send us space-based observatory or telescope? Why it wasn't possible to do from the ground like we have some many other telescopes? So uh, before we go why, let us see what are the instruments or what wavelengths this Astrosat observatory instruments are observing. So there is a X-ray, large area X-ray counter instrument. Then there is a ultraviolet imaging telescope, and then there is a hard X-ray measurement instrument, and then there is a scanning sky monitor. And then, so this is basically for sky surveys. And then there is a soft X-ray telescope. So now you'll see that, okay, and in addition to this, this also has some optical instruments as well. So you'll see that it's mostly X-rays and ultraviolet, hard X-rays. So these are mostly high energy radiation or wavelengths. So why was this need of a space-based observatory? So you may have heard that, okay, whenever you say light, we generally mean that it's the visible light that we see. But light or electromagnetic radiation has also many other wavelengths. So we may have heard these terms like radio waves, microwaves, or X-rays, gamma rays. But if you see that, so here the radio waves which have the longest wavelengths but lowest in energy, and as you move right, you are increasing the energy but decreasing the wavelength, or you are increasing the frequency. Okay, and here you have the visible band. This shows some real life objects, which gives you the idea of the scale of the wavelength of those particular bands. Now you'll see that here some terms are there, yn. So it basically tells whether these wavelength bands can penetrate the Earth's atmosphere and reach us on the ground. So, for example, in radio waves, yeah, certain radio waves can reach ground. So that's why we have radio telescopes. Then microwaves, no, some of it get absorbed, some does reaches on the ground. Then infrared, so again in infrared, some reaches the ground, and some of it gets absorbed by the water molecules in the Earth's atmosphere. Visible band, more or less, everything comes to the surface. And then ultraviolet, X-rays, and gamma rays. So all of these get either absorbed or decayed in the atmosphere. So, if you want to study the universe in these high energy bands, you don't have any other option other than going above the atmosphere. Okay, and that's why space based telescopes or instruments are required. And so the earlier astronomy, when it started, so it was limited to the visible light or optical bands, what is called. Okay, but as our technologies improved, as we started having instruments which could measure other wavelengths also, for example radio waves or infrared or X-rays, so it was realized that the universe is not limited to visible bands. Universe is also emitting radiation in different bands, and if you monitor these different bands, you will get to know about processes which could be or totally different, or it could be new science. So if you want to study universe, rather than studying only say visible light separately or say X-rays separately, it is important to do what is called as multi-wavelength astronomy. That means you study the universe in multiple wavebands. So as an example, here it is what is called as Crab Nebula. It is a supernova remnant. A star died almost 1,000 years ago, and it is a remnant of the outer shells of that particular star. And here you can see the appearance of the Crab Nebula. It is different in different bands. Okay, so when you monitor the same object in different bands, it tells you about different kind of processes, different kind of physics that is happening over there, and it can tell you or give you new insights about the same object. So that's why it is important to do what is known as multi-wavelength astronomy, and that's why India launched this Astrosat mission, which was monitoring or which can monitor objects in high energy bands. And so in 5 years of operation, it has observed more than 1,000 targets and objects. There have been more than 150 research papers, and the observatory is not only being utilized by Indian scientists, it is also being utilized by scientists outside India. So it's a productive instrument. And so if you go to the ISRO website that I have shown here, you will get many more details about the observatory and the mission, and you'll also come to know like how the proposal is submitted, and like if you are interested to do some sort of some specific science, or if you want to monitor some particular object, so it can be for sky surveys, or it can be to monitor objects which are called as transients, which give out light over a short period of time, and then it decays or changes, or some variable objects which give whose light or radiation output changes with time. So such kind of objects are being monitored by this observatory. So this was one talk.
Virendra, yeah,
Yeah.
yeah.
Hello.
I was just curious. As we all know, that the Astrosat was really a very successful mission. So,
Mhm.
is ISRO planning any other mission in this X-ray or gamma region in the future?
In fact, there are talks of Astrosat 2. So, and
Okay,
there
okay,
were so for example, other space-based observatories, or rather space-based missions around, say, other planets. So they also had different instruments. So for example, if you take the case of Mangalyaan or Mars orbiter mission, so uh, there were different kind of instrument which were rather than measuring the light output. Of course, there were instruments which were also measuring, say, ultraviolet rays or something like that, but there were also particle analyzers. Basically, they were measuring what is the kind of particles, or what is the composition of the atmosphere in around Mars. So this so depending upon your science goals and interest, different instruments are planned and different missions are planned. So right now there are talks of Astrosat 2, is what I came to know from the ISRO's webpage, if when I went to gather information about the Astrosat mission. Now, there was another one very interesting talk about a future telescope projects. So quickly, we have heard that, okay, you use telescope to look at the stars and galaxies or planets far away, because these are very faint objects. They give very small amount of light. So that's why you need larger area to gather that light. So essentially, telescopes are light buckets. They collect a lot of light so that even faint objects can be seen or observed. So basically, there are two types of telescope: what is known as a refractor containing lens, and another type called as reflector, which contains mirror. And so this is and depending upon whether you are interested in hobby observations or slightly more astrophotography kind of observations, uh, and whether you are interested in observing planets or deep sky objects, so depending upon that, you can choose a telescope suited to you. Okay. But when it comes to telescopes, bigger is always better, because the larger the area of your lens or the mirror, the more light you collect. Okay, so it is similar to like collecting, say, rainwater in a glass and, say, a bucket. So you are going to collect more water in a bucket rather than, say, a glass. So similarly, you equate the light photons with rain, and the size of the or diameter of the glass or the bucket with the diameter of your telescope. So that's why bigger is always better. Now, when it comes to astronomy, so all of these, or rather the recent ones, are always mirror based telescopes, because very old times, like late 19th century telescopes used to be lens based, but there were disadvantages when you used bigger and bigger lenses in observatories. So the telescopes were almost becoming too long to manage and too heavy to manage, and there were different issues with the optics quality also. And so with the advent of technology, they started telescopes with only mirrors. And then as the time progressed, as our technology progressed, mirrors started getting bigger and bigger, and the observatories started getting bigger and bigger. So just for as an example, uh, these are some of the optical band or near infrared wavelength telescopes that are operational in India right now. So, for example, this is a telescope where I work at present. It's a 1 meter telescope. The diameter of the mirror is 1 meter. Then there is one operated by PRL in Mount Abu, that is about 1.2 meters. And then there are 2.34 meter Venu Bapu telescope operated by IIA in Kavalur, Tamil Nadu. And located at one of the best sites for astronomy or doing astronomy, the 2-meter Himalayan Chandra telescope in Hanle. Why the best site? Because this is almost like 4.2 kilometer above or 4.3 kilometers above the mean sea level. So you are at very high altitude. So you are above most of the water vapor content of the atmosphere. The water vapor content in the atmosphere is mainly limited within about say 2 kilometers or so from ground. So if you are above that, the locations are really, or the sky that you get over there is really really useful for astronomy, rather than if you are say on ground level or just maybe within a kilometer or so. So, and plus it's also a region, it is very dry, it is very cold, and it's a very remote region, so you don't have any light pollution at all. And so because of that, it's for astronomy it is an absolutely wonderful location. And you also get something like 300 nights or so clear sky nights, yeah, in a year. So the more number of nights that you have, the more observations or scientific observations you can do. So it is one of
Please
the
tell
best
us
sites.
about the, yeah.
Yes.
Do tell us about the now planned, more
Yeah,
recent
yeah. So
endeavors.
I'm coming to that. So now,
And
at present, the largest one is this, the 3.6 meter Devasthal telescope, Devasthal optical telescope. It is operated by Aries, the institute where I work, and it is located about 50 kilometers away from our main campus. And this again is a bit remote location, but the advantage there is that the altitude over here is about 2450 meters from mean sea level. So you are above the most of the water vapor content in the atmosphere. So it's a really good location for doing astronomy. And so this is the view of the telescope from inside. The diameter of the mirror is about 3.6 meters. And for comparison of uh, say something real life objects, so here is a plastic chair that we use in our households. So you can compare the size with this. And it's rather, a bit difficult to compare the or appreciate the size in this photo, because it's a wide angle photo, so there is some curvature over here. But it's really mesmerizing when you see it in person. And the entire structure is something like 149 tons. And so in the center of this structure over here, there is a huge concrete, solid concrete pier, and on top of that over here the telescope is situated. So, but if you see that these telescopes, although this is the largest telescope in India, and uh, in a way
yeah,
effectively the largest usable telescope within Asia, or most of the regions in Asia, but it is still much smaller than most of the largest telescopes which are already operational for something like 1 or 2 decades, or even 3 decades globally. So some of these telescopes are located in on Mauna Kea Peak in Hawaii, or in Atacama Desert in Chile. So again, these are very dry sites, very cold sites, and located away from light pollution. So these are good for again for doing astronomy. So you can see that astronomers want to go as big as possible to collect as much light as possible, so they can detect as faint sources as possible. But going bigger and bigger has its own challenges. Making a single mirror, because as the size increases, its thickness also will increase, and the weight also will increase. And after a certain time, the mirror will become so huge and its weight will be so huge that the mirror will get distorted under its own weight. So if you try to move it, the shape will get distorted and it will be useless for astronomical observations. But they say that necessity is mother of invention. So an invention was made, and people came up with something called as segmented mirror. Now, what is this segmented mirror? I'll come to it in a bit. So, for example, this image that it is there, it compares many of the famous and the presently operational large telescopes. So here, so for example, here you can see this is the Hubble Space Telescope. It has a diameter of about 2.4 meters, and for comparison, here is a human in the same scale. Here it is a tennis court, and here a basketball court. And then you can see that here you have a Hooker telescope, which was about 1 meter, and then a 2 meter telescope, which was operational in USA, so in 1917 and 1948. So you can see that 2 meter class telescopes have been there since nearly 1950s, and around say 1996. So here you can see that in 1996 they have had come up with nearly 10-meter class telescopes in 90s, and so in 90s and 2000s there were many 8-meter to 10-meter class telescopes operational. So although a lot of good science came up from that, they still wanted to go bigger, and that's why these global projects came up in which many countries are taking part. So here you can see this is called as 30-meter telescope, because the diameter of the telescope is 30 meters. Then there is something called as extremely large telescope. This has been modified to European extremely large telescope, which is going to be near about 42 meters. And long back there were ideas or proposals just in concept stage to make a telescope with 100-meter diameter, known as overwhelmingly large telescope or owl telescope, but it has been scrapped because the cost was,
We
as they say, astronomical.
we will
So
need to
yeah,
conclude.
yeah,
We will,
just two more
yeah,
slides.
yeah, yeah.
So India has been part of this 30-meter telescope. So India will be having access to this, and India is contributing about 10% of the project, and many of the Indian research institutes are part of that. And India also will be building some of these segments, or making some of these segments. But India doesn't have its own any 8 to 10-meter class telescope yet. But since India is already taking part in this 30-meter telescope, and India will be making some of these segments along with other countries, so we are gaining the technical know-how and the technology for this. So there are plans of making an 8 to 10-meter class telescope of our own that will be located in Hanle. And the 30-meter telescope projects, there is a optics fabrication facility which has been already been established in Bangalore by IIA. So for example, here they are inspecting a mirror that was arrived from Japan, and how these segmented mirrors are. So this is again from China, which is another partner in the project. So it shows like how segmented mirrors are. So basically, segmented mirrors are like a jigsaw puzzle. Okay, you have small segments, and then you attach them, and you make a big mirror out of that. So what is the advantage? That you don't have to make a very large mirror at one go, okay, which can be very heavy and which can be damaged because of its weight. But you just make small segments, and then you just connect them. But it's not a very easy job. So behind each of these segments, you have many uh, what is called as actuators. So these are basically devices which move your telescopic segment, so that overall you can align them in such a way that all of these segments form part of a single mirror, and they behave like a big single mirror. Okay, and so there are different techniques that are being developed and utilized to do all these kind of alignments. And once everything will be done, so it will be like here you can see as an example, there are three different segments, but the entire telescope is behaving like a telescope with one single mirror. Okay, so this is what being planned right now. Yeah, that's it.
Thank you for taking us through the instrumentation plans. And yeah, there was we were planning to have discussions about the solar system, which probably solar system session, sun and solar system sessions, which probably we will do tomorrow.
Okay.
And I'll see if there were any questions. And also, I think one of the next sessions, Manonita, would you come in for the, since we are not doing the sun solar system today, but perhaps tomorrow, with the stars, ISM, and the galaxy talks, what were discussed there. And where is this power? Yeah, I'll remove that. And Virendraji, would you be okay with staying on and making it our the next session interactive?
Yeah, sure.
And who who were planning to do the next session? Let me just see. Manonita, Manani, and Gunjan, right? Can I add you in?
Uh, I
Uh,
I am already there.
yeah, yeah, yeah. So your video, Gunjan. Let me add Gunjan.
Yeah,
And
and
if
Ashwin will
anyone else would like to come in for the discussion, please keep your video on. I will know that you want to come in for the discussion.
Ashwin.
Yes. And have I added everyone who wanted to be part of this discussion? Manonita, you are there. So you want to bring our participants up to date about the some of the afternoon sessions, stars and ISM and the galaxy. Manonita, shall I hand over to you to set the ball rolling?
Okay, sure. Thank you.
Yeah, with your talk on the magnetars, maybe if you want to
Yeah.
tell
So I can
participants about what are magnetars and get us started that way.
right. So I will start with my own talk. If possible, I would like to share my screen. If that's okay.
Sure, sure. You can share your screen and I can add it in.
Mhm. I will show only very minor pictures, but still, I think it would be.
Oh, I have not added one of me. Oh,
Mm.
yeah, yeah. All right. And
Is
so
it working?
let me just see. Yeah, yeah, yeah. Now let me add your presentation. Yeah, it is there. It is there. You could even click on that hide so that that little bar which is there at the bottom will go away. Yes,
Right.
please go ahead.
Yeah. So basically, this discussion it's about magnetars. They are absolutely fascinating objects. So magnetars are a type of neutron stars. Neutron stars are the end remnants of stars. So when the stars run out of their fuel, particularly if they have masses from 8 to 20 solar masses, they end up forming neutron stars. And a class of these neutron stars have a very high magnetic field. By high, I mean about 1,000 trillion times the magnetic field of Earth. So here you can see a completely artistic representation of such a new magnetar or a neutron star with such high magnetic field. And these lines that you can see are shows the magnetic lines of force that shows the strength of magnetic field and the direction of magnetic fields. And since the stars have these strong magnetic fields, such magnetic fields guide how the stars will emit and how they will behave, what will be their change in their properties. For example, these magnetars are also pulsars. By pulsars I mean they show periodic intensities of radiation, and these periodic intensities of radiation are completely affected by the corresponding changes in the magnetic field. And this particular object shows the most strongest magnetic field in the universe. So that gives us a very unique opportunity to study what would happen when we look into what how strong magnetic fields behave, how particles in strong magnetic field behaves. So this is such a scenario. So we are studying different magnetars, particularly a specific property of magnetar. What is that? The specific property of magnetar we are interested in is the flares. So it's like a very bursting event or a flaring event that happens in the case of magnetars. Why does this happen? So this is something very similar to what you see in the solar flaring events. So it's completely thought to be related to the magnetic field of the magnetar. So the idea is that inside the magnetar there is very strong magnetic field, and often what happens is inside the fluid that is inside the stellar crust, the magnetic lines get distorted and builds up lots and lots of stress. And as the stress develop, they 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 build up very strongly, and they can get attached to the crust of the crust of this star, and can break up the star because they are kind of attached to the crust itself. And uh, as they break the crust, it's like the earthquakes that you see on the surface of Earth. Kind of similar to that, but more related to the effect of the magnetic field in this case. And as they break up the crust, all the stress, all the distorted energy that was developed is kind of thrown away in terms of this bright flaring events that you see. And this is often guided by how the magnetic field lines behave. Magnetic field behaves in the region where the crust has broken or the crust had fractured. It's like earthquake on the surface of neutron stars. So, or earth fissure developed due to earthquake on the surface of the neutron stars. So this is kind of similar to what happens. So you have such neutron stars and or magnetars, and the lines that you see, the magnetic lines of force, they get twisted, and as they get twisted, they try to come back to the most comfortable position. And as they try to come back to the comfortable position, they kind of tear back the crust that is happening, and that results in a lot of radiation getting released in such crust breaking events. So this is very this radiation that you see in the cases when this crustal fracturing or this fracturing of the neutron star surface occurs, it's very, very bright because the magnetic field that you have in hand is also very high. It's so bright that the corresponding radiation that you receive, the first event, or one of the brightest cases of the such event that was discovered, when it was discovered, the satellite that discovered it, it was not even looking at the particular star. It was looking in a complete different direction. But the radiation, which happens in this case in gamma rays, was so intense that even if when the satellite was not directly looking at it, it completely flooded the detector. And this radiation in gamma rays can be very, very high energetic and can be one of the most brightest events that you see in gamma rays. This gives us a very good handle to study, first of all, this
So
exotic.
I just want to ask a question for clarification over here. So this flaring event that is there, it is not due to the breaking of the magnetic field lines that like we see in the case of magnetic reconnection, in the case of say solar wind interaction with the earth, but rather the magnetic field is so strong, or rather the magnetic tension is so strong that the crust itself is teared up, okay, from or the material on the surface of the magnetar is teared up because of the force is so strong, overcoming
So,
the gravitational field of the star. Am I correct?
so that's an excellent question. The answer is a bit of both,
Okay.
meaning both models are used to explain the such a scenario, and we till now don't know which one is the correct. So
Okay.
I kind of roughly gave an idea of the both, didn't clearly specify, but you were very correct. It's
Okay.
basically talking about two different scenarios, and both can explain such scenarios,
Okay.
and both have been put forward to explain such bright flaring events. And
Mhm.
using the theoretical concepts of both, we can actually explain the properties in both cases. Hmm. So both can be possible.
Okay.
Ideally, reconnection is now put forward a lot, but we still are not at that stage. We can favor one over the other. So
Okay.
yes, you are very correct. We can talk in terms of solar flares. We can talk in terms of earthquakes. Yeah, and one of the such brightest events that was seen is this particular flare, which was seen from the magnetar. This particular magnetar, this was seen in.
Are you sharing your screen? I think it has
Yes.
stopped sharing.
Oh, I'm sorry. Is it working?
Uh, Ratnashri madam, are you there?
Yeah. I'm just trying to
Okay, okay.
see
Sorry,
where
it's
it
my
is in the
fault.
studio. Yeah, it's not in the studio just now. Could you
Okay,
share it again? Could you share? Yeah, it's there.
okay, okay.
Okay.
Sorry about that. Yeah. So one such flaring event is this one. So what happened is that in gamma rays, but it was observed that from this particular magnet in 1998, the intensity increased by orders of magnitude when this flaring event happened, and reached very high values. It increased by about 1,000 times at least. Hmm. And after that, for a long period of time, about few hundreds of seconds, the intensity remained quite high and decayed over a slowly period of time. The total energy that was released in this was very high, and that is uh, decided by how the flaring event happened. And this intensity up and downs that you see here, this basically gives the spin period, the how first the planetary itself is rotating. Okay, so such flaring events, particularly this type of very bright flaring events where the brightness can reach um, to um, yeah, to very high values in terms of solar luminosities. One can say it reaches about, I am forgetting the exact number, but it reaches many times the solar luminosity. So those kind of flaring events, the brightest one till now have been detected in only 3 cases from magnetars. Only 3 such scenarios we have detected. And thus it makes them very exciting events. They are only seen in the very high energies, gamma rays. They are very bright and they show very exotic behavior. So one would ideally like to understand them bit more, and try to see whether this can be used to explain any other phenomena in the universe. So, with that in mind, let's talk about, if I have 2 more minutes, 3 more
Okay.
minutes.
Yeah, sure,
Okay.
sure.
Yeah, it would complete in 2 minutes. Yes.
2 3 more minutes. With that in mind, let's talk about a very interesting thing that happens, which is called the gamma ray bursts. What are gamma ray bursts? Gamma ray bursts are very high energetic explosions that happens in the gamma rays. They can be quite long meaning they can be more than few seconds, or they can be very short, few fraction of seconds. They are very interesting because they are related to the point when the star, usually, particularly the long ones, are related to the time when the star is undergoing its death. Or, in other words, when we say that the star is collapsing to form a neutron star or a black hole. Now, there can be the short gamma ray burst also, and you must have heard of the gravitational wave discovery recently, right? And the gravitational wave discovery was attributed to two black holes merging with each other. So spinning round and finally colliding and merging with each other. That such as event was also observed for two neutron stars colliding and merging with each other. And when these two neutron stars merged and collided with each other, one could observe such bright flaring events in gamma rays. So, and which lasted for this kind of short durations of time. So, for the short gamma ray burst, it's thought that they are getting originated when these two neutron stars are merging, or a neutron star is merging with some other, possibly black hole, but most likely neutron star. So we are getting very strong gamma ray emissions, and that leads to formation of further exotic events. This was the rough idea behind short gamma ray bursts. Now, what we are proposing, that maybe some of the short gamma ray bursts that is related when two neutron stars merge with each other are not always related to this merging event, but maybe some of the short gamma ray bursts are of the magnetar giant flares, because both are bright in gamma rays, both are very intense, and also we showed in our studies that they have various properties. Oops, sorry. Oops, sorry, I'm so sorry.
So,
Uh,
so, since one of these events at least, there was clearly a signature of neutron stars coalescing, right?
yeah,
And
right.
then why are we kind of what are the signatures which are saying that we are identifying it with another process now?
Yes, yeah, right. So the signatures depends on a number of properties of the gamma ray bursts. Huh. One important property is, first of all, they can be associated with a galaxy. So we know what are the kind of stars there, what are their ages, what are the star formation rates. So we can expect such magnetar systems there. That's the first thing to start with. And this particular case that we are talking about can be very well related to a nearby galaxy. In this case, a galaxy called as Sculptor galaxy. Apart from that, the total energy content for gamma ray burst has a very strong dependence on the maximum energy during its peak. And for this particular flaring event that we are saying that it's actually a giant flare, it was very different from the classical gamma ray burst that you see, short gamma ray burst. Its total energy was different, the way its intensity varied was different, and the amount of radiation and how it cooled over time as the flare decayed was also different and more closer to that you see for the giant flares. And it shows a very long tail like behavior that you see, for example, uh, here. Here you can see a long tail. So the short gamma ray bursts that we saw showed such a long tail, and whatever the radiative and whatever the intensity variation patterns that we see in the case of such giant flares was observed in the case of this particular short gamma ray burst, which has lasting duration of few fraction of seconds, and was actually observed last year in April. So we've showed that this was not the classical merging kind of two neutron star scenario, but instead of that, possibly it's most likely to be one of these magnetar flares which are coming from this crustal fracturing or the magnetic reconnection, uh, like you see in the case of solar flares. And this kind of short gamma ray bursts, which are likely to be giant flares, their properties are more closer to giant flares, have only been shown for 3 to 4 cases. So given the scenario, we are uh, hoping that most of the other gamma ray bursts, not most, but at least a fraction of the other short gamma ray bursts that you see, may also be giant flares of magnetars rather than merging of two neutron stars, because merging of two neutron stars is very nice scenario, but that that is the probability of two neutron stars being there in our orbit and merging is not as high as all the short gamma ray bursts that we see all in our observations, the rate of short gamma ray bursts in an observation. So these giant flares can help to explain why we see so many short gamma ray bursts, so on and so on.
Do you always expect a burst following, like a tail following the burst
In the case
for
of flare,
magnetars?
in the case of magnetar flares, yes. For the very short ones, we cannot say much because it's very weak to detect. But for the relatively brighter ones, definitely we see such very strong outer afterglows or long tail emissions, which are very characteristic of the magnetar flaring events.
Okay, you don't say it any other object, right? Like it's
Not like this, not the specific, not having this specific property of that you see in the case of
Yeah, so
magnetar.
basically, flare is basically it shoots up, I mean, shoots up like anything and then drops exponentially. That is the tail that we are essentially talking about now,
Uh,
right?
Not exactly, because in this case, the tail lasts for much, much longer duration.
Mm-hmm.
So it's
I
not
see.
just an exponential downfall, but
Okay.
it's a steady emission for a much longer period of time. And that relates
Okay.
to how the fracturing or the reconnection is happening at that particular site. And
So
that
can you
also we
take?
study in details in our book. Yeah,
Yeah,
sorry.
and
can you tell
if I
on what time
sorry.
scale it happens? Sorry, the reconnection time or the change in the crust, how long it takes to happen? Can you put a constraint on that with the how long the tail is?
The tail is not necessarily, I would say, uh, linearly correlated with the crustal scenario,
Time
because
period, right?
following that, the relative processes, sorry for using some technical terms, but following that, how the emission will behave and all the charged particles that were created, how they
Hmm.
will behave, that will guide how long the tail will behave,
Okay,
how long the tail will be, and how bright the tail will be.
right.
There is a question from viewers not related to this but to stellar evolution,
Sure.
and wanting to know how CNO reaction is maintained in a star. And so, would any of us take that up? And then we can move on to the things
Sure.
that you are discussing. So, CNO reaction maintained in a star, basically, these are kind of like just maybe sun or little more massive stars than that.
No.
These
Uh,
reactions are happening, right?
yeah.
And
We need a
carbon, nitrogen,
supermassive
oxygen
star
are
as
being
well.
used as catalysts, so they are not they are remaining there, while hydrogen is getting consumed and helium is getting produced. So it's when
Right, it just
hydrogen
forms
is
layers like onions, right? So the outermost layer has hydrogen burning, the second in the most layer has helium burning. As we go further deep inside, there are these complex nuclear reactions which permit the higher elements to form. So then it keeps on continuing till iron forms in the core in a much more massive star. And
Right, but that may not happen always for CNO cases.
correct. So it depends on the temperature as well as the
Temperature
pressure
greenhouse. Yeah.
that choose the
So for
scenario.
sunlight star, it will initially start with the PP chain, because the you have to have a sufficient temperature to allow these fusion reactions to go on. This is a fusion reaction of two hydrogen nuclei to form a helium nuclei. The easiest chain is the PP chain, which can happen at a relatively lower temperature. But if you make the stars a little bit more massive, the central temperature becomes even higher. And as it becomes higher, it goes from the PP chain to the CNO chain, which still fuses hydrogen to form helium, but through a slightly different route. And in this route, it requires carbon, nitrogen, oxygen, which helps us to more efficiently fuse the hydrogen nuclei to form more and more helium. So that's how a CNO cycle is maintained. In short, you need a little bit more temperature to begin with.
So Shri, you had a question.
Yeah, I have a very basic question. These gamma ray bursts are they the super flares we see, like very rare? Like Are these called super flares or something else?
Mm, mm. They are, to my knowledge, they are not necessarily called super flares. But what we are saying, the couple of short duration gamma ray bursts can be thought of the super flare, can be explained by the super flares coming from the magnetar sources, which are highly magnetic neutron stars.
Okay. Because like these super flares occur very rarely. So in comparison to the solar flares that we see, so I
Ah,
mean,
okay, I understand.
so that's why I
Are you
asked.
talking about the super flares in sun?
No, no, no. Like the first one that was detected by Carrington, that was, I mean, he draw it in a, he draw it by observing it directly. So like from that, that was the like biggest flare that is recorded till now. So after that, we don't see like mostly the X class flares. The flares are categorized in different I mean, they
These
are
are
categorized according to their energy. So the X class are the largest one. So the super flares are all, I mean, the larger, even the larger than these X class flares. So that's why I asked.
Yeah, can I just mention something over here because I am a
Yes,
bit
sure.
aware with what you are asking. So,
Yeah.
what process Manonita has just described. So, these are actually many order of magnitudes stronger than what we see in the sun's case. Okay, solar flares are. I mean, if the kind of flare that she was describing, it if it occurs, as close as the sun is to us. I mean, it probably blind us. It may be so strong. So,
Yeah.
and even the solar flares or the large flare that occurred during the Carrington event, yeah, there it is not the largest even in the life of say a sun-like star. It so happens that when stars are developing or the star is very young, it has just started forming. So in the nascent stage of a sun-like star, uh, the space weather events that occur that time and the flaring activity occurs that time, it is much more frequent and much more stronger than what we see for middle age star like the sun is. So if we say if we were there on Earth, or if the Earth was there, say probably 4 or 4.5 billion years ago, when the sun was pretty young, so at that time the flare activity would have been much more frequent and much more stronger as compared to the say Carrington event.
Oh, okay. But the Carrington
But
event
these are
was like,
minuscule.
sorry?
But these are minuscule as compared to what Manunita was
Yes, yes,
describing.
yes. Okay, okay. Okay, okay, thank you.
To all of you, if you have any kind of questions, connections, etc., for whatever was discussed, maybe we could have that, but probably not start a discussion of another topic or talk altogether because we have run so much out of time. So we could
Yes.
take those any additional topics which we had been planning to have discussions about today. We will move them to tomorrow, right? And but
That
if
was
you have any questions about whatever has been discussed or any inputs, etc., kind of to wrap up, and to tell the viewers and come in again tomorrow if you have any of these questions. um, you can post them here before we end the broadcast today, but you please do be at, this is a continuing session tomorrow as well as day after at the same
Yeah.
time. Yeah. So, any of you, if you would like to add some questions, inputs before we wrap up? Uh,
I think
So,
some of you were planning something. Are you going to do tomorrow?
yes, yes.
Yeah, I
Tomorrow,
think
this activity is going to last
I,
for another 2 days.
2 days. Actually, I think some of the students who are present were planning to discuss many of the sessions which happened today. But because we have run out of time, I'm just asking that let's regroup again tomorrow to do those discussions about any of the sessions that you found interesting and you want to talk about. So, Manonita, there is this question. I mean, we of us could take, but what are the major sources of gamma ray burst? Meaning, what are the major kind of connections that we have, which we say are giving rise to gamma ray bursts. So one you already, I mean, you talked about
Yeah.
the possibility of magnetars, but maybe and you also talked about the possibility of neutron stars coalescing,
Yes.
and so these any other possible sources?
The other one that I mentioned is briefly, but that's more useful for the long gamma ray burst, which are lasting for a few seconds. So that is when just a massive star is collapsing, undergoing
This will
supernova.
be a very large supernova.
Yeah, exactly. Exactly. Those are associated with long gamma ray bursts. So those are the classical gamma ray
Yeah,
bursts.
yeah. So three channels, three of these channels. All right, Priyabrata. Hope that answers your question. If anybody has any other, they could just post it quickly on the YouTube. And I would like to thank everyone who was there in the discussion today to kind of make user friendly some of the. I mean, there have been so many. I mean, it's a huge meeting, right? There is so much, and there is no way, of course, we are going to be able to do justice to
Cover
so much of
everything.
content which is covered. But these Astro sessions we have, so over the coming year, we will try and have some of these sessions as full-fledged talks.
Yeah,
So,
yeah,
in fact, we'll take the ASI meeting as a kind of our source for getting Astro talks. So,
yeah,
in
yeah.
a year, maybe we can try and cover everything which was discussed in these popular talks. So thank you everyone. We will all regroup tomorrow. All of you will be there, right?
Yeah, yeah.
We will
Yeah, yeah,
regroup
sure, man.
tomorrow.
Yeah, yeah.
And
We
so
will.
either any of the talks which happened day before yesterday or yesterday or today or tomorrow, we will
Yeah,
just
sure.
do that. Thank you everyone.
Thank you everyone for joining.
Thank
So
you.
I will. Do I see any other question? No. Okay. All right. So we will end this and the broadcast. Thank you everybody.